Now I will discuss the grouping of capacitor like you people have done in class 10th, combination of resistance. So firstly, capacitors are said to be connected in series if charge on each capacitor is same. So I am writing the very brief definition. When charge on each capacitor is same, then you will say they are connected in series. Like here, there are three capacitors of capacitance C1, C2 and C3, and they are connected to a supply due to which charges is plus Q, minus Q, plus Q, minus Q, plus Q, minus Q, and so on. So if we write the equation, we can say potential at point A, suppose I say that is VA, then drop in potential at capacitance C1 you will say minus Q by C1, at C2 capacitance it is minus Q by C2, then minus Q by C3, and we are getting potential of B point. So we can say VA minus VB can be written as Q 1 upon C1 plus 1 upon C2 plus 1 upon C3, and we say this is the equivalent circuit. In this equivalent circuit, if I write the equation VA minus Q upon C equivalent equal to VB, I can say here VA minus VB Q into 1 upon C equivalent. If I compare this equation number 1 with this equation number 2, I get the standard result, that is 1 upon C equivalent equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3, like this. Now one more thing I want to tell here. Suppose I short a capacitor in this series combination. Let me solve in the next slide. That will be better. So I am discussing the shortening of a capacitor. In series combination. Suppose I say exactly same situation which I was discussing in the last slide. There are three capacitors of capacitance, I say C1, C2 and C3, like this, and I connect to any supply, and I say the supply is having the voltage V. I connect like this, in this way, and when this series connection, I will say charge is same, plus Q minus Q plus Q minus Q, so I write here only Q. You people get the idea, it is plus Q minus Q plus Q minus Q. And suppose I take the thin conducting resistance-less wire and I connect to this capacitor C2. This is the thin conducting resistance less wire. I generally say we are shunting it or bypassing it. So ultimately we are shorting C2. Now I write the equation. If I say this is the point A, this is point B, what I will say, VA minus VB equal to, directly can I write Q by C1 plus Q by C3, and when I compare the ideal or equivalent resistance, I can say 1 upon C equivalent is written as 1 upon C1 plus 1 upon C3. So I have discussed both the thing, equivalent capacitance, when not shorting, when there is shorting. Now I will display in the coming slides capacitance combination when it is connected in series. Okay, so there are three capacitors C1, C2, C3 connected to supply, and as we know charge will be always same because it is series combination, and of course potential difference is different. I am showing same charge, voltage is different, and you can solve in this way or what I have discussed in the last slide. Both are true. So this is the formula. I think we have to increase the slide width. Now I will discuss the connection of capacitor in parallel. So we will say, so I write capacitor are said to be connected in parallel combination if potential difference across each capacitor are same, because they are connected to same positive and negative end. I say in this situation, let me connect it. Potential at it and this end is VA, this end is VB, and charge Q is supplied. This charge split into Q1, Q2, and Q3. Now I write the equation. Then first I write from this path VA. Then voltage drop is given by Q1 by C1. This must be equal to VB. Then from this path VA minus Q2 by C2 equal to VB. Then from lower path VA minus, there is some trouble, VA minus Q3 upon C3 equal to VB. Now here I say Q1 equal to written as C1 VA minus VB. Second equation gives me Q2 equal to given by C2 VA minus VB, and third equation gives me Q3 equal to C3 VA minus VB. Is it okay? And this is the equivalent circuit, circuit. Here I write the equation VA minus Q upon C equivalent equal to VB. So I write Q equal to C equivalent VA minus VB. Now I can say Q equal to Q1 plus Q2 plus Q3. Put the value of the Q, put the value of the Q1 top, yes, Q2 and Q3. And what you will get? You will get the result C equal to, that is given by C1 plus C2 plus C3. This is C equivalent. Now I am showing on the next slide. There are three capacitors. They are connected to a supply. Now in parallel combination, all of us know potential is same across each capacitor. So charge is different. So you can do in this way also. Then you put the value of the Q, Q1, Q2, Q3 and get the result like this. Okay, before this I will discuss the shortening in the parallel capacitor also. Let me do in the next slide. So now I will discuss the shortening in the parallel system also. Suppose I say there are three capacitors. First I draw the diagram. This is the circuit diagram like this. Okay, and here I say this is capacitor C1 capacitance, this is C2, this is C3, and you connect supply at A point and B point. So we say potential is V and VB, and by chance you short this capacitor. Now the charge Q will come through the positive side and it will follow the bypass path. So what we will say, if we make the equation is VA minus VB equal to 0. It's clear? Or you can say V in equivalent circuit, VA minus Q by C equivalent equal to VB. And if you compare both the equation, you can say C equivalent is infinite. In parallel capacitor, if you short any of the capacitor, net capacitance become infinite. I hope it is clear to you. Now I will discuss capacitance of a parallel plate capacitor. Just a minute. So capacitance of a parallel plate capacitor. Suppose here we consider two parallel conducting plates, and each of area A, is say area of each plate is A, and they are separated by a small distance, that is D. D is the distance between the plates, and we say that the charges are plus Q and minus Q, like this. Now we assume the Gaussian surface, like I say this is the Gaussian surface, a closed box like this. You assume it is a closed box. Box means you can assume it is just like a cuboid. It must be backside also, like this. You have to close it. Now this box is such that you will say whose top surface is inside the upper conducting plate, like this, and inside the upper conducting plate all of you will say electric field is 0 inside the conductor, and bottom face is between the plates where we say electric field is constant. Now if I ask you what is the electric flux through the side face of this imaginary Gaussian surface, yes, you will say it is 0. Why? Because electric field is normal to the area vector. Electric field is towards the negative axis and area vector is taken as plus x-axis. Now flux linked through the top face is also 0. Why 0? Because E net is 0. So we can say only bottom surface contributes the flux. So I write the Gauss law, integration E dot dA equal to Q enclosed by epsilon naught. This must be vector, no problem. Now you will say EA equal to, in this Gaussian surface charge is plus Q, Q by epsilon naught. So electric field can be written as Q by epsilon naught into A. Now we all know dV is written as minus E dot dr. We all know very well. Now potential difference when you move from the lower surface to the top means 0 to D, and in this situation 0 to D we say E and dr both are opposite. That is visible to all of you. So you will say dV can be written as minus minus plus 0 to D E dr. Now I can write E equal to Q by epsilon naught A into dr, like this. Integration limit from 0 to D. What we get? We get Qd upon epsilon naught A. Therefore capacity can be written as Q upon potential difference. You will put the values, you will get the result epsilon naught A by D. I think there is some problem in software, so please bear it. So all of you will get the answer C equal to epsilon naught A by D. Is it clear to all of you? Again I am telling you, we are not getting the term charge, we are not getting the term delta V in this expression of the capacity. So we will say capacitance of an ideal parallel plate capacitor depends only on the geometrical factor, that is area of the plate A, distance between the plate small d. I hope it is clear to all of you. Now you can think in another way also. I will explain you another approach also. Just think that. Suppose you say same diagram, let me put here. You can think this parallel plate like the above diagram, or same thing you can think in this fashion also. Like you say there are two plates, one plate near to another plate, you give the Q charge here, you ground it, and all of you know as you ground it, on this surface plus Q charge and this surface minus Q charge will come. Exactly same situation. Why I am showing you? So that you can get resemblance of these two figures in numericals. Okay, so if I ask you electric field between the plates, all of you will say E equal to, I think there is again some trouble, E equal to sigma by epsilon naught. I hope it is clear. Let I take a point A on the positive plate and at a point B on this plate. Okay, now if I write potential difference, of course we people know the formula dV equal to minus E dot dr, that we know very well. I integrate it, and you are moving from plate A to plate B, you will see here potential is VA, here potential is VB. Okay, and you are moving from A to B, I write A and I write B. I integrate it and I solve it. I think we will get VB minus VA equal to minus E, and this distance between B minus A, I say it is D. So this is the potential difference. I can say V equal to minus E into D. And what is given regarding E? E is given you sigma by epsilon naught, and sigma again you will say charge per unit area, like this. Now you know the formula. You will say C equal to Q by V, and you will get epsilon naught A by D. And of course I will discuss in detail, but just here for your knowledge, if we completely fill with the dielectric, in place of, I say, in place of air or vacuum, I put a dielectric, then capacitance is given by epsilon r or K, epsilon naught A by D. Capacitance is K times. And again I am revising you, please keep this in mind. A is the overlapping area, means suppose plates are like this. This is the plate of area A1 and this is another plate of area A2, like this. In the numerical, area of the plate will be taken A2 because there is a overlapping area. Is it clear? Now I am showing you on the slides capacitance of a parallel plate capacitor. Just you pause the slides, pause the video and read it, whatever I have explained you. This we have done just now. This we have discussed. And this I have discussed in electric field also. Again I am showing you. So if any numerical comes, any questions come, you can visualize the numerical or question. Okay. Now I am discussing energy stored in a capacitor. Okay. I say this is a capacitor and it is connected to a supply like this, V volt. Suppose at any instant there is some charge here. Capacitor, sorry, this should be minus. This side is plus. And at any instant, this is the charge Q, this is charge minus Q. Now if you give another charge from this battery, suppose I am taking another positive charge from this battery and this charge is entering in through this wire. Now you just think it, I am explaining here only. This is the positive plate and another charge is going. All of you know the charges which are on this plate A, that will repel it. They will not allow to enter this charge into the plate. It means you have to apply some force, and that force should be equal to the force applied by this plate. It means work is doing by the battery because force is provided by the battery. And we know whenever there is force, whenever there is displacement, always there is work. So we say work is done on sending the charge on this charge plate. Again next charge, next work, next charge, next work, so on. So battery's energy is spending in doing the work, and that energy is transferring to the capacitor. I hope how the energy stored in the capacitor concept is very much clear to all of you. Now, at any instant, charge I say Q, and let I say voltage is V. And if I give small charge dq on same voltage, then I say work done is given by V dq, and I will say V can be written as Q by C. The net work done I calculate W is given by, you can integrate it, I think I can leave, this is an exercise for all of you. You will say Q square by 2C. This work convert on capacitor to its potential energy, which I say U equal to Q square by 2C. Now my question is that where this energy in the capacitor? Yes, you have to say energy resides in the electric field between the plates, because you know if it is a plus Q charge, if it is minus Q charge, the energy resides between the plates like this. I hope it is clear to all of you. No one has any doubt in it. Sometimes you have to calculate the energy density also. Let me explain that also. Energy density, energy per unit volume. You will say energy, you can change this formula in number of way by applying Q equal to CV, you get half CV square also. So I say it is half CV square upon volume. Capacitance, if I use parallel plate capacitor, generally we use that only, epsilon naught A by D, and volume can be written as E into D, that also you people know very well, and this is the volume, and this is the potential. Potential, let I write small v, so you will get a little bit idea, and potential is given by E into D. When you put here, energy density will come half epsilon naught E square, that you will get. Now, one more thing I want to tell here clearly. You know kinetic energy K equal to half mv square. All of you know it. Power of the material is mass. Power of the material is mass. You know spring energy half K x square, and power of the spring is K. Similarly, in capacitor U equal to half CV square. C is the power of the capacitor. Okay, is it clear to all of you? Similarly, in inductor you will read later on, energy is given by half Li square. L is the power of the inductor. It means you can keep one thing in mind, energy is given by half into constant, that is the power, into variable square. Everywhere mass is constant, spring constant is constant, capacitor is constant, inductor is constant, but all of you know velocity is variable, displacement is variable, potential differences may be variable, and this current may be variable. Is it clear to you? Now, okay, so I am showing you on the board, please go through it. Okay, there is some trouble. Energy stored in capacitor. There are two plates connected with the supply, getting some charge. So you just pause the video, read each and every slide, because we have discussed in theory this derivation. Q equal to CV, use the Q equal to CV, you get these formulas. Energy density also I have told you, half epsilon of E square. You will solve it. Energy per unit volume. Series combination I have discussed, so you can do it on your own. This is the for series combination. Parallel combination. Okay. Graphical analysis. You just recall the graphs which you have drawn in class 11th in the potential energy spring half kx square, something like that. Same thing I am telling you. If we have the graph, all of you know energy below the graph gives the energy. Sorry, area below the graph gives the energy. Now, this area gives energy. Why? Because if I say area is given here, graph is between voltage and charge. So this whole shaded, suppose I say this is whole shaded part. Please think this only. Let me draw it, so you will get better idea on the next slide. Okay. So energy is given by half base into height. I say here base is given. This is the base, like this. Then this is total height in this right angle triangle. And energy is the area in this graph. Half, you will say that is Q into E, and Q itself is CV. You are getting half CV square. So sometimes you have to think with the graphical method also. Is it clear? Okay. Now I will discuss this in the next video.